Okay, we're going to do some videos for radical expressions, equations, and functions. Got some objectives here. We're going to first talk about what a radical expression looks like. And we've got this right here. It's showing us the three parts of a radical expression. The first part being this little number up here in the corner. We call that an index. The number underneath the symbol is called the radicand, and the symbol itself is called a radical sign. Now sometimes we don't see any number up here in the corner. When there's no number there, it indicates that the number is implied to be 2. A radical sign is an operation. The operation is asking you to find a specific number. The index tells you how many of factors that will multiply together to make 8. For instance, this expression is asking us for the cubed root of 8, or what number, when I use it as a factor 3 times, multiplies together to make 8. If we look at these examples here, the square root of 16, this is asking us for 2 factors that will multiply together to make 16, and of course that's 4. This one is asking us for the cubed root of 64, and I know this is a cube because of the index 3, or what number, when I use 3 of them together, multiplies to make 64, and that's 4. This expression is asking me for the fourth root of 16, or what number, when I use it as a factor 4 times, will equal 16. And if you didn't know that, that's the number 2. 2 times 2 times 2 times 2 equals 16. We're going to simplify a few of these expressions here. If you're using this book, you can see the answers are already input for you. However, we can figure them out for ourselves. The square root of 49 is asking me for what number, when I use it, and the index here is 2. When I use it twice, 2 factors identical together make 49, and that's 7. The square root of 121 is 11, because 11 times 11 is 121. The square root of 100 is 10. 10 times 10 makes 100. And the square root of 36 is 6. Here on the next page, the first example we see is actually, I'm going to rewrite this example, the square root of a fraction. And I know a fraction can be scary for some people, and a lot of you guys will avoid the fractions when you see them, but it doesn't have to be as difficult as it looks. It really is the same as looking for the square root of the numerator and the denominator separately. When you write it like this, you don't have to even think about a fraction. You just think about simplifying, okay, the square root of 9, which is 3, and in the denominator, the square root of 25, which is 5. So you can see the square root of 9 over 25 is 3 over 5. The next example has a negative sign in front of the radical, so I'm going to rewrite that. This really, again, this negative sign being outside the radical has no effect on what happens in the radical. So that negative sign is just going to carry over right there to the front, and then you're just going to simplify inside the radical just like you did before. The square root of 49 is asking you for what number, when I multiply it times itself, makes 49, and that is 7. So this turns out to be negative 7. We read this as the negative square root of 49. The negative sign comes straight over. The square root of 49 is 7, so the answer is negative 7. The next one down here is a little bit different. It says the square root of negative 81. Now, to think about this, what this is really asking you for is what 2 factors, identical, when you multiply them together, will give you negative 81 as their product. And you could try multiplying negative 9 times negative 9, but when you multiply a negative times a negative, it comes out to be a positive. So the square root of negative 81 is not negative 9, because negative 9 times negative 9 gives us positive 81. In fact, there are no two numbers identical when I multiply them together that will give me negative 81. So for now, we're going to say this is not a real number. Further on in the chapter, we'll talk about imaginary numbers, which is what this is, and we'll define what imaginary numbers are then. But for now, there is no square root of a negative number that is a real number, so this is not a real number. To go down here to example 2, we can look at the note at the top here that says, for odd indexes, the radicand cannot be negative. The radicand can be negative, excuse me. For odd indexes, the radicand can be negative. For even indexes, the radicand cannot be negative. So we'll try these. This is letter A. The fifth root of 32. What number, when you multiply 5 of the same number together, will give you 32? One thing that's true when you're working with these, the higher the index is, the lower your root will be, because you have to have 5 of them multiplied together to make 32. If you get stuck here, the best way to figure this out is by using the tree and prime factor your 32 down. Of course, two numbers that multiply to make 32 are 8 times 4, and then when I factor these down again, I get a whole bunch of 2's. When I circle all those 2's, those are the prime factors of 32, and you actually do notice there are 5 of them. 1, 2, 3, 4, 5. 5 2's multiplied together make 32. So the fifth root of 32 is 5. Next example is the fourth root of 81. What this means is, what number, when I use 4 identical numbers to multiply together, will give me 81. Kind of a shortcut for finding the fourth root is to find a square root and then do square root again. That would be a fourth root, 2 consecutive square roots. We know the square root of 81 is 9. 9 times 9 is 81. But then the square root of 9 is 4. So the fourth root of 81 is 3. The square root of 81 is 9. The square root of 9 is 3. So the fourth root of 81 is 3. The next example says the cubed root of negative 8. Now we talked about the cubed root of a negative number is not a real number, because there are no 2 identical numbers that will multiply to make a negative. But this is a cubed root, which means we need 3 numbers multiplied together to make negative 8, and that would be perfectly fine, because if you have 3 negatives multiplied together, it does give you a negative. The cubed root of 8 is 2. The cubed root of 8 is negative 2, because negative 2 times negative 2 times negative 2, 3 of them, gives you negative 8. So if you have an odd index, it's perfectly fine to have a negative number in here. The root comes out to be negative. If you have an even index like 2, this negative under here tells you this will not be a real number. And if you look at example D, you can see that. This is the fourth root of negative 256 is not a real number, because when you use 4 negative numbers multiplied together, it comes out positive, not negative. So this fourth root of a negative number is not a real number. On letter E, we have the sixth root of 1 over 64. So let's write that. The sixth root of 1 over 64. This is the same as doing the sixth root of 1 over the sixth root of 64. The sixth root of 1 is 1. Any root of 1 is always 1. The sixth root of 64, and if I use the tree on the 64, I could break it down just like I did the 32 up here. It comes out to be 5 2's. So the sixth root of 64 is 2, and so the sixth root of 1 over 64 is 1/2. We're going to do another fraction down here. The fourth root of 16 over 625. The fourth root of 16, and like I said before, kind of a trick for doing fourth root is to do square root, then square root again. The square root of 16 is 4, because 4 times 4 is 16. The square root of 4 is 2. So the fourth root of 16 is 2. So the numerator up here will be 2. The fourth root of 625. If you don't know, the square root of 625 is 25. 25 times 25 is 625. And if you have a calculator available to you, that can always help you with some of these big numbers. The square root of 625 is 25, and then the square root of 25 is 5. So this denominator will be a 5. Down here, when we look at letter G, we see there's a negative sign outside and there's a negative sign inside. Let's rewrite this. The negative cubed root of negative 343. All right, this negative sign outside is not going to do anything. It's just going to transfer right over into our answer. So let's just put that negative sign in there. This negative just transfers straight over. Then we have to think about the cube root of negative 343. Is this a real number? Well, since this index is odd, then yes, it is a real number, but the root is also going to be negative. So we're going to have another negative over here. So we're going to put that in here with some parentheses. And I happen to know that when I put 343 cubed root into my calculator, it comes out to be 7. So the cube root of negative 343 is 7. Negative 7. So I end up with these two negatives here. This one coming straight over from outside the radical, and this one coming from having a negative inside the radical. The cubed root of a negative number is a negative number. Now you can simplify these two negatives, and of course, that will make a positive. So down here, further on down the page, we have a little explanation here. What happens when the index is the same as the power or as an exponent? The radical goes away when the expression has the same index and the same exponent. The quickest way to simplify such an expression is to look at the index. So if you look at this example here, you have the square root of 5 squared is equal to 5. Why is that? If you think about this, underneath this radical, 5 squared is 25. The square root of 25 is 5. This exponent 2 and this radical cancel each other. And they will, as long as the index, which here is implied to be 2, the index and the exponent are the same. You do have to be careful with negatives, though, because in order of operations, this operation would come before a radical. So when you square a negative number, negative 5 squared is positive 25. The square root of positive 25 is positive 5. So you have to be careful when you have negatives under here. When you look down here at the cubes, this index and this exponent are the same. They cancel each other on a positive base. So the cubed root of 4 cubed is 4. But the cubed root of a negative number, does that continue to be negative? Think about what happens when you cube a negative number. If you have a negative times a negative times a negative, 3 negatives multiplied together, it stays negative. So this base under here will still be negative, and the cubed root of a negative number is a negative number. So the difference between this one becoming positive and this one staying negative is the fact that the index and the exponent are odd or even. With even indexes and exponents, the negatives multiply out. But with odd numbered indexes and exponents, the negative stays, and so the result becomes negative. On example 3, we're going to simplify some of these. So we have the fifth root of 4 to the fifth power. Well, since these are both positive, the fifth root index and exponent cancel each other, and the result is 4. On letter B, we have the square root of 3 squared, and again, the base being positive, the index and the exponent are the same, so they cancel each other, and the result is 3. On letter C, we have the square root of a negative base being squared. So we have to kind of think about this with the negative numbers. When you square a negative 16, I don't really know what 16 squared is. It doesn't really matter though. When I square this, it will be a positive number, and then when I take the square root of it, it will go back to 16, but it will be positive 16 because the negative multiplied out. On letter D, I have the cubed root of 5 cubed. No negatives here, so these index and exponents cancel each other to give me 5. On letter E, the cubed root of negative 6 cubed. Thinking about the negative, when I cube a negative, it stays negative. Negative times negative times negative gives me a negative base here. The cubed root of a negative base is negative, so this will be negative 6. On letter F, the fourth root of 8 to the fourth power. Again, no negatives here, so you know these same index and exponent will cancel each other to give you 8. On letter G, the fourth root of negative 7 to the fourth power, and we need to think about this negative because there are 4 of them. 1, 2, 3, 4 negatives multiplied together give you a positive number. And the fourth root of that positive number will be positive. These 4s do cancel each other, and the base becomes positive 7. Letter H, the sixth root of a negative number. And again, with an even index and an even exponent, these negatives multiply out when there's an even number of them, and 6 is even, so this will become positive, and this result will then be positive 3. On letter I, the square root of x squared, the index and the exponent cancel, so we will just get x. On letter J, the cubed root of x plus 1 cubed, and we're going to use this concept a little further on when we're solving equations, but this index, this exponent cancel, and the result will be x plus 1. Okay, on the bottom of this page we have some approximations. When simplifying numbers that are not perfect squares, cubes, fourths, or fifths, we can use a calculator to find decimal approximations. We express the answer using the approximate symbol, and here it is right here. It looks like a squiggly little equal sign. Use a calculator to simplify the following expression and round your answers to 3 decimal places. Alright, I don't have a calculator example in front of me to show you guys how to enter this in your calculator, so we'll do this in class when we get there, but you can practice it looking for where the square root symbol, the cubed root symbol, and these other symbols are on your TI 83 or 84. Make sure you bring them to class. TI 83 or 84, and we'll go through the steps in class how to simplify those. Alright, when we we simplify radical expressions, and this can be a little complicated, we look for factors of what we're trying to simplify. So here we're trying to simplify the square root of 98. We look for a factor of 98 that is a perfect square, and that would be 49. 98 is 49 times 2. We can simplify the 49. We separate these, the 49 and the 2. The square root of 49 is 7. The 2 that cannot be simplified stays under. This is a cubed root of negative 54. We can separate this into negative 27 times 2. And the reason we're using negative 27 is because 27 is a perfect cube. It's 3 times 3 times 3. The negative sign, because we know it's okay to take a negative cubed root, so we separate this into 27 times 2. The cubed root of negative 27 is negative 3. The 2 stays under. On letter C, we have a square root. The square root of 4x cubed y to the 5th. Now, all even exponents are perfect squares because we take a square root of an exponent by dividing by the index, which is 2 here. So you can separate these up. This is not really the way I like to do it. I'm going to zoom in here and show you how I like to do this. I will first look at the coefficient, which is a perfect square. I know the square root of 4 is 2, so I'm going to write a 2. And then I'm going to put my radical way over here. And then I'm going to look at this exponent, this variable. I'm going to divide by the index. How many groups of 2 can I make out of 3x's? Because 2 is the index here, so I'm looking for 2 factors. 2 goes into 3 one time, so that will give me 1x on the outside. But that doesn't use up all the x's. 2 goes into 3 one time, but that only uses up 2 of the x's, and there will be 1 left over. That 1 left over will go in here. So it's a little bit about mental division, if you can do the mental division. And then you go here again with the y. 2 goes into 5 2 times, so we'll have y squared out here. That's how many groups I can make, but again, that doesn't use up all the y's. 2 goes into 5 2 times, but that only makes 4 y's, so that 1 extra will be left over in here, and so I'll put it in here. I'm going to do the same thing down here with this one. The square root of 81 is 9, so I'm going to put a 9 on the outside. Then I'm going to put my radical here. The index is 2. How many groups of 2 can I make out of L squared? Well, I can make one group of 2. So that would be 1L for one group on the outside. But there are no leftovers. All of these are used up with my one group, so no leftovers in here. How many groups of 2 can I make out of 3M's? I can make one group, and there will be 1 left over. How many groups of 2 can I make out of N7? 2 goes into 7 3 times. So there'll be n cubed out here and 1 left over because that doesn't use up all of them. 2 goes into 7 3 times, but that's only 6 and 1 left over in here. So 9L m n cubed square root of m squared. Down here, same thing, except now the index is 3. So I'm going to make groups of 3. First of all, -8 is a perfect cube. I think we talked about this on a previous page. The cubed root of -8 is -2. And then I'm going to put my radical over here, but I have to remember if the index isn't 2, that I have to write that index in there. So I have an index of 3. Then I make groups of 3. How many groups of 3? In a to the 6, there are 2 groups of 3. No leftovers. How many groups of 3 in b to the 10? There will be 3 groups of 3 with 1 left over. And again, 10 divided by 3 is 3 with 1 left, 1 remainder. How many groups of 3 in c to the 14? Well, 3 goes into 14 4 times, but that only makes 12, so there'll be 2 left over on the inside. Okay, so we're looking for a 4th root now of 32, and once these indexes get a little bit higher, you really need to probably use the tree to find your groups of 4. So I'm going to zoom in, and I'm going to use the tree on the 32. (32) is 8 times 4. Oh, we've done this one before. But what do we end up with? We end up with a bunch of 2's, don't we? All right, there are 5 2's here. 1, 2, 3, 4, 5. But I only need a group of 4. 4 of these 2's will come to the outside as 1. The 4th root, and this will be a 16, will be a 2. But then this 1, 2 that doesn't get into that group of 4 is going to have to stay on the inside. So if we start to write this, there'll be a 2 on the outside, and then with our leftovers, there'll be a 2 on the inside. And then we start looking here. How many groups of 4 can we make out of u cubed? Well, 4 doesn't go into 3. There's not enough to make a whole group. So the whole thing is going to have to stay here in the leftovers. So we're going to have a u cubed here in the leftovers. Out of v to the 4th, we can make one group of 4. 4 goes into 4 one time, so there'll be one v here on the outside. You just scroll over a little bit here. How many groups of 4 can we make out of w to the 5th? We can make one group with 1 left over. How many groups of 4 can we make out of y to the 7? We can make one group, but there will be 3 left over. So we have 2vwy times the 4th root of 2u cubed wy cubed. All right, on the next one, we're looking for the 5th root of 32. We just used the tree on the 32, and they gave us all these 2's, and actually there's 5 of them. So to make a group of 5, it would just be the whole group of 2's coming to the outside. We won't have this one left over anymore. So we're going to have a 2 on the outside, and I'm going to set up for my leftovers right over here. Now I'm making groups of 5. How many groups of 5 can I make out of u cubed? Well, I can't make even an entire group, so the whole thing is going to have to go in here. So u cubed. How many groups of 5 can I make out of v to the 5th? One group of 5, no leftovers. How many groups of 5 out of w to the 5th? One group, no leftovers. How many 5's in y to the 7? 1, but I'll have leftovers this time. Because that only uses up 5, I'll have y squared left over, or 2 y's left over. 5 goes into 7 one time with 2 left over. All right, so we're going to do the 6th root of 128, and I'm going to do that over here to the side again. I'm going to use the tree on the 128. 128 is 2 times 64. 64 is 8 times 8. 8 is 4 times 2. 4 is 2 times 2. 8 is 4 times 2, and 4 is 2 times 2. And we're going to circle all those prime numbers. There's a 2, a 2, 2, a couple more 2. Oh, they're all 2's. How many? 1, 2, 3, 4, 5, 6, 7 2's. I only need a group of 6. So these 6 can come to the outside as a 2, but this 1 will be left over inside. So we're going to set it up here. 1, 2 on the outside, and a 2 left on the inside. And then we can start dividing our exponents. How many groups of 6? Well, I can't even make a whole group of 6, so this has to all stay inside. I like blue better. B to the 4th. Same thing here. I can't make a whole group, so the whole thing has to stay in. W to the 5th. How many groups of 6 can I make? I can only make one group here, so I'm going to have 1y, and there will be 1 left over. So I'm just going to move this 2, please, over here, just closer in. So the 6th root of 128 gave us a 2 on the outside with a 2 left on the end because there were 7 in the whole group. This has no groups. I can't make a full group, so this has to stay. Same with this one. I can make one group out of this, but there's 1 left over. So this is what I end up with. Example 6 is applications or word problems. In order to clean a 20-foot high window, one of our Osceola maintenance persons, Lorenzo, needs to put a ladder 8 feet away from the building. How long of a ladder is needed for this job? So if you can recognize, the window is here, it's 20 feet up. The ladder is 8 feet away from the building. So this is the side of the building, this is the ground, this is the ladder, 8 feet away from the ground, leaning up here to the window. This makes a right triangle. When you're looking for a missing side in a right triangle, you use Pythagorean's theorem, which is a squared plus b squared equals c squared. A and b are the two sides that make the right angle, and c is the longer side. In this case, it's the ladder. So we're going to use 20 for A and 8 for B, and we're going to fit them into the formula so we can solve for C over here. So that would be 20 squared plus 8 squared equals C squared. And we're just going to simplify. 20 squared is 400. 8 squared is 64. To find C squared, we add them together. 464 equals C squared. Now, we don't really want to know C squared, we just want to know C. So to get rid of this square, we're going to use a square root, but we have to do the same thing to both sides. So we're going to put a square root on here, and that will give us C. And it looks like this is not a perfect square. So you can just put this into your calculator and give an estimation either to the nearest foot or maybe to 1 decimal place. When you put that in your calculator, that comes out to be about 21.5, or to the nearest foot, 22 feet. So the ladder needs to be approximately 22 feet long. You can see all of that work here, but we're going to go down to the next one. On Denjon Lane, there's a wall with a sign that has the college's old name on it. The goal is to update the sign that is 30 feet tall, so this is the sign, with the college's new name. The maintenance person's Marco has a ladder that is 40 feet long. How far away from the wall does a ladder need to be in order to reach the sign? And again, this makes a triangle, but this time we know A, we don't know B, we do know C. So we're still going to use Pythagorean's theorem. A squared plus B squared equals C squared. But this time we will fill in A, not B, and C. So A is 30. So we're going to have 30 squared We don't know b, we do know c is 40. And then we will simplify and solve for b. So 30 squared is 900. 40 squared is 1600. To solve for b, we're going to have to isolate this, so we'll subtract this 900 on both sides. That would give us b squared equals 700. Then to solve for b, we'll use a radical to get rid of that square. We'll get b equals approximately 26.5. So the ladder needs to be about 27 feet away from the wall. All right, on this page we're just going to evaluate radical functions. So we've got three functions here that have radicals in them. We've got f of x is the square root of x plus 2, g of x is a cubed root of x minus 4, and h of x is the fourth root of x minus 1. And we're just going to go down through these few examples. We're going to use f for the first three, and then we'll use g, and then we'll use h, just replacing what we're trying to evaluate into the function. So to find f of negative 1, we're going to use the f of x function. F of x equals the square root of x plus 2. To find f of negative 1, we'll replace negative 1 for x right in here. So we'll have negative 1 plus 2, or the square root of negative 1 plus 2. And then we simplify. Negative 1 plus 2 is 1, so this is the square root of 1, which is 1. So f of negative 1 equals 1. To find f of 0, again, we're going to use the same function. F of x equals the square root of x plus 2. To find f of 0, we put the 0 in, we replace x with 0 in the function. We have the square root of 0 plus 2, which is the square root of 2. So f of 0 equals the square root of 2. To find f of 2, we're going to use the same function. F of x equals the square root of x plus 2. We will replace 2 for x in our function. So f of 2 is going to equal the square root of 2 plus 2, which is the square root of 4, which simplifies to make 2. Now we're going to move on to g. This is a new function, g of 12. I'm going to have to scroll back to the top to find out what the function is for g. Here's the function for g. G of x is a cubed root of x minus 4. So when I use it, I'm going to write it here. G of x is the cubed root of x minus 4. So to find g of 12, I'm going to replace 12 for x in this function. So g of 12 equals the cubed root of 12 minus 4. I don't really need that parentheses there. 12 minus 4 is 8, so this would be the cubed root of 8, which is 2. 2 times 2 times 2 equals 8. Okay, so letter E is asking us to find g of 3. So again, we're going to use this g of x function. G of x is the cubed root of x minus 4, and I'm going to replace 3 for x in this function. So g of 3 equals the cubed root of 3 minus 4. 3 minus 4 is negative 1. The cubed root of negative 1 is negative 1. Remember that the cubed root, any odd index of a negative number, is a negative number. Negative 1 times negative 1 times negative 1 makes negative 1. I'm going to find g of 6. So I'm going to write the g of x function again. G of x equals the cubed root of x minus 4. And I'm going to substitute the 6 for x. So g of 6 equals the cubed root of 6 minus 4. 6 minus 4 is 2. I can't simplify that cubed root of 2 any further, so g of 6 equals the cubed root of 2. Now I'm going to move on to h. So I need to go back and refer. What is the h function up here? H of x is the fourth root of x minus 1. So the fourth root of x minus 1. I'm going to write the h function here. H of x equals the fourth root of x minus 1. So h of 1 substitutes a 1 into that function. So h of 1 equals the fourth root of 1 minus 1. Well, the fourth 1 minus 1 is 0, and any root of 0 is 0. Now I'm going to find h of 7. So h of x equals the fourth root of x minus 1. So I'm going to substitute the 7 for x. So h of 7 equals the fourth root of 7 minus 1. 7 minus 1 is 6. The fourth root of 6 cannot be simplified. There are no perfect squares or perfect fourth root factors inside 6, so this is done. It cannot be simplified any further. This last one, h of 82. The h function, h of x equals the fourth root of x minus 1. So we're going to put the 82 in the function for x. 82 minus 1 is 81. The fourth root of 81, and earlier I said there's a trick for fourth root. You just take square root and then square root again. The square root of 81 is 9. The square root of 9 is 3. So the fourth root of 81 is 3. So h of 82 equals 3.